The azimuthal equidistant projection map is typically seen centered about the geographic North Pole. The further you get from the center in one of these projections, the more distorted the landmass gets from reality. Here, I have the map projection centered on my house. You can make one centered on anything you like with the azimuthal equidistant map projection generator I've linked into the description. Some individuals believe the North Pole-centered azimuthal equidistant map projection accurately represents the Earth, and that the masses have been, or the people, we've been deceived into believing it's spherical, or something like that. By this logic, I guess we have also been more specifically deceived into believing that Australia is smaller than the continent of North America, and that Russia and Canada are the largest countries by landmass. And of course, they are the largest countries, but not on this projection map. So, this belief has greater implications than just landmass, shapes, and sizes, and I'll get into that in, I guess, throughout the video, actually. The flat Earth theory looks quite bad when you take into account that the geographic poles and the magnetic poles are separate of each other. The geographic poles are the furthest points from the equator, and the magnetic poles are the points based on the Earth's magnetism. The Earth is like a dipolar magnet, which is the most stable type of magnet. On the flat Earth model, the Earth is portrayed as a radial magnet, which is a relatively unstable magnet. The magnetic poles have been observed to wander over time, actually quite quickly, many miles per year. You can look up the exact location of it currently and the speed it's going presently, but I didn't get into that. The wandering indicates a certain fluidity, and fluidity would likely allow a radial disk magnet to reorganize into a dipolar disk magnet, a more stable state. Either way, we observe a polar wandering, and I think it looks really bad on the flat Earth model. The seasons are caused by the Earth's 23.5 degree tilt upon its rotational axis. From the spring equinox to the fall equinox, and especially during the summer solstice in the northern hemisphere receives more direct sunlight. It is warmer, and the days are longer. During the winter, from fall equinox to spring equinox, the northern hemisphere receives less direct sunlight. It's cooler, and the days are shorter. The sun never directly faces anything outside of 23.5 degrees south and 23.5 degrees north. On the flat Earth model, the sun takes a circular path over the disk. During the summer solstice in the northern hemisphere, the sun moves at a slower speed and takes smaller circles. During the winter, the sun moves faster and takes larger circles. In the next section, I'll talk more about the sun's appearance and its relative path through the sky. Right now, I'll talk more about the length of days. Here, I created a viewing window. As you take the viewing window to points further from 90 degrees north, the length of the day, delineated by the map, begins to conflict with reality more and more. Here are a few examples. According to this map, Japan has roughly 12-hour days throughout the summer and 7-hour days throughout the winter. In reality, Japan has 14.5-hour-long days in the summer and 10-hour-long days in the winter. When you put the viewing window around or over New Zealand, it gets really bad. So, where according to this map, New Zealand has roughly 6-hour-long summer days and 5-hour-long winter days, in reality, New Zealand has 15-hour-long summer days and 9.5-hour-long winter days. This is significant, so wrap your mind around it. Alright, I'm moving on. I don't know what flat earthers think of the Coriolis effect, but I can explain it. I can explain what it is. Basically, the Earth is rotating counterclockwise. A point at the equator has to go faster than, let's say, a point at 60 degrees north, because they both have to go around the same axis in 24 hours, but the point on the equator is further from the axis than the point at 60 degrees north. If a substance with fluidity, like air or the ocean, moves north or south, it'll maintain some of its forward speed from its previous point or place, meaning that if an air mass is moving from south to north in the northern hemisphere, it'll maintain its speed from the more southerly point, resulting in a veer to the right. In the northern hemisphere, fluids always veer to their right when traveling from north to south, and in the southern hemisphere, fluids always veer to their left. In the northern hemisphere, this results in hurricanes and extratropical cyclones spinning counterclockwise, and ocean gyres and areas of high pressure moving clockwise. Even if flat earthers settled on the earth being like a record on a record player, that still wouldn't explain why the Coriolis effect works in the opposite way in the southern hemisphere. Now we'll talk about the sun's appearance and its relative path through the sky. In reality, the sun takes a roughly straight path through the sky to those living at the equator. As you get further from the equator, the path the sun takes, relative to you, appears more circular, and as if it is going around you. Finally, at the poles, during their respective summers, the sun does not set, but makes a 360-degree circle in the sky. In the northern hemisphere, the contention with reality is not as great as it is in the southern hemisphere. Here, I have a compass over Japan. During the summer solstice, on the flat Earth model, the sun rises in the northeast. At solar noon, the sun is at its highest altitude, indicated by its proximity to Japan. By the way, altitude is just its angle to the ground. Then the sun sets in the northwest. This correlates to reality to an extent, but place the compass over New Zealand and things get really bad for the flat Earth model. During the summer solstice in New Zealand, on the flat Earth model, the sun rises in the northeast. At solar noon, it is due north, then it sets in the northwest. In reality, the sun rises in the east-southeast. At solar noon, it sits due north, then it sets west-southwest. In reality, the Earth is a sphere. During the summer, in the southern hemisphere, it faces the sun, more so. The conflict is greatest at the South Pole, where in reality, the sun rises once, sometime in mid-September, and sets once, sometime in mid-March, causing the South Pole to receive indirect sunlight, or some sunlight, for 6 months out of the year. And, tell me how that's possible on the flat Earth model. How can the South Pole receive sunlight for 6 months? That really needs some explaining. I don't see how that's remotely possible. But I guess I can move on to the sun's appearance as it moves through the sky. In reality, the sun does not appear to change in size as it rises, peaks, and descends. This is explained really easily by the current model of understanding. The sun's distance from the Earth is so great that a point's change in proximity to the sun between sunrise and solar noon is negligible. I've looked at many sources that talk about the sun's distance from the Earth on the flat Earth model and concluded that they believe the sun to be, about 500 to 5,000 miles above the surface of the Earth. I calculated the distance from Tokyo, Japan, to the point where during an equinox the sun would be directly overhead as it also began to peak or set on the horizon in Japan. From there, I just did relatively simple math to find the size of the sun over the course of the day relative to an individual standing in Japan. I made the size of the sun at solar noon 100%, so the size of it at the horizon is inversely proportional. As distance increases between the points where the sun is directly overhead and the point where the sun is at the horizon, the percentage denoting the size of the sun at the horizon decreases. As we can see by my calculations, if the sun was 5,000 miles above the surface of the Earth, it would only appear to be 2/3 the size in the morning than at solar noon. The apparent change in the size of the sun would be very great if it were only 500 miles up. That's a greater change. It would be a greater change than tenfold Call it whatever you like. There is a testable force that pulls objects towards the ground at 32.17 feet per second squared. That means, if you drop an object, for every second that goes by, it'll fall 32.17 feet per second faster. This isn't always the case. Objects still have to deal with buoyancy and air resistance, but for the most part, this is the case. Also, density does not determine how much something's going to fall. So basically, density is just a unit of measure. It has no force to pull it up or down, and buoyancy is actually the equation to figure out buoyancy involves gravity, so that just doesn't work. Drop 2 water bottles. Try that. An empty one and a full one. They will hit the ground around the same time. This force, which is typically regarded as gravity, is the reason why air pressure is greater at sea level than in the mountains, is the reason there is such a thing as buoyancy, like I said, and is the reason why objects fall to the ground and stay on the ground. Gravity causes objects to tend towards a center of mass, and it takes energy to pull objects away. I've heard flat earthers try to explain away gravity by saying the Earth is constantly accelerating upward, in which case an ascending object would never descend but be caught by the Earth. Of course, this is observably untrue. Just throw an object up into the air, watch it rise, stop, and then fall back down. Most flat earthers just seem to think objects descend because down is just down. I don't know what kind of reasoning this is, but yeah, it doesn't really make sense to me. Why is down down? The sun and moon both exhibit an observable force on the oceans. These forces are called tides. During full and new moons, the tides globally are greater. You have lower low tides and higher high tides. These are called spring tides. During first and third quarter moons, the tides are observably smaller. The variations are smaller. These are called neap tides. Most places experience 2 high tides a day and 2 low tides. These are called semi-diurnal, and they are the types of tides you'd expect to see being parallel with the moon. Places that experience 1 high tide and 1 low tide a day are called diurnal, and places that experience sort of an in-between or sort of mix of the two is called mixed semi-diurnal. And diurnal and mixed semi-diurnal are caused by the the ocean's interaction with land, the seafloor topography, centrifugal force, and the Coriolis effect. Where does the moon get its light from? The moon receives sunlight and reflects some of it to the Earth. Just like the Earth, half of the moon is always illuminated. The phases of the moon that we see here on Earth are caused by the moon's position relative to the Earth and Sun. If you see the moon in the morning, it's waning. If you see in the evening, it's waxing. And if you see it around midnight, it is full or close to being a full moon. Some individuals have the misconception that lunar phases are caused by the Earth's shadow. The only time the Earth's shadow is seen on the moon is during a lunar eclipse. I know flat earthers believe the moon generates its own light. So, what is the energy source, or what is the fuel being burned that produces the light? I don't know. They believe the moonlight is cold, just like the sun's light is warm. This is untrue, but it's a neat idea nonetheless. In nature, everything tends to have its binary, or have its, opposite. But sunlight's opposite is not moonlight, because all light's opposite is darkness. Flat earthers also tend to believe the Earth is translucent or transparent, something like that, and that's why it appears blue during the day. Of course, in reality, the atmosphere is subject to Rayleigh scattering, and the moon lies beyond the atmosphere. Rayleigh scattering can be observed on a smaller scale in, metal colloids. They scatter light the same way, particles in the atmosphere do. Now I'll move on. What is a lunar month, and when do eclipses occur? When you think about a lunar month, you probably think about the length of time between two full moons. This is known as a synodic month, and it is the amount of time it takes the moon to be in the same position relative to the Earth and Sun twice. The time it takes, 29 days, 12 hours, 44 minutes, and 2.8 seconds, is useful in determining phases and eclipses. An eclipse can only happen during a new moon or full moon. The next kind of lunar eclipse, or the next kind of lunar month, is the sidereal month, and it is the time it takes the moon to complete a 360-degree revolution around the Earth, or to be in the same position relative to the stars twice. The synodic month is longer than the sidereal month because the Earth revolves around the Sun counterclockwise and the Moon revolves around the Earth counterclockwise. The sidereal month is useful in determining the Moon's relative position. A tropical month is the amount of time it takes the Moon to be at the Earth's latitude 0 degrees twice. It's slightly shorter than a sidereal month because the Earth's axis practically revolves on its own axis clockwise. The tropical month is useful in determining the Moon's relative position. An anomalistic month is the amount of time it takes the Moon to be at the furthest point from the Earth twice. It's slightly longer than the sidereal month because that furthest point moves around the Earth counterclockwise. The anomalistic month is helpful in determining whether a solar eclipse is going to be annular or total. The fifth and final lunar month is used to determine whether a new moon or full moon will be an eclipse or not. It is called a nodal month. Because the moon's orbital plane is tilted to the plane at which the Earth receives sunlight, there are only 2 points where an eclipse can occur. Those points are called nodes. The amount of time it takes the moon to visit one node twice is the length of a nodal month. It is slightly shorter than the sidereal month because the moon's tilted plane revolves around the Earth clockwise. An eclipse is possible roughly every 5.5 to 6 months when the nodes are between the Earth and the Sun. To be fair, all of the lunar months take part in determining the moon's relative position. I try my best not to talk over heads. Sometimes these concepts can be hard to wrap our minds around. I pretty much just mashed a bunch of stuff I know together. I'm completely impartial to information I'm given. I seek truth because I'd rather walk in light rather than darkness. If you have faith in Christ, and the idea of the globe weakens your faith, then your faith is not built on solid ground. It looks to me like you use a lie to gird the truth. Why don't you study Christian apologetics or theology or something, so you can truly fight for what you believe? Most of this video, I just presented you with observable facts that go against the flat earth model. I could probably make another video like it, and I could make a video talking about how the Bible is used to defend flat earth and the history of the flat earth model. Through the production of this video, I felt a bit down. Seems to me like a lot of flat earthers have made their minds, but, also this hits real close to home too. I have family members that believe this. So, I don't believe I made this video in vain. I don't really like debate stuff. It doesn't seem to be very productive, but this video in particular I don't think I made uselessly. If you're a flat earther and you'd like to debunk my video, do so as you please. I'm not gonna care. Use whatever you like. Use as much of it as you'd like. And then post a link in the comment section of this video, and I'll even pin it to the top. If multiple of you guys do this, then I'll just have to copy the links and put them into one pinned comment of mine. But either way, I'll pin it to the top of the video. Yeah, my only request is that you find another facts-based video of mine that you do agree with, because I'm sure there is going to be one in there, and give it some publicity. Alright, thanks for watching.